Today we will study the famous Faraday's law of electromagnetic induction, which is the fundamental for all further chapters of electricity, alternating current, how EMF is induced and many other features. Okay. This is based on experiment what you have seen in the previous lecture. The law made on the basis of that experiment is law number 1, change in magnetic flux linked to a coil induce an EMF across the coil. This is magnetic flux linked to this coil, and if there is a change due to its motion, then an EMF is induced. Whenever there is an EMF induced between the 2 points, the EMF is induced between the 2 points. If we close this circuit by fitting a galvanometer, then what is the job of an EMF? It produces current. If there is a path given to it, the current will flow through it. Okay. So, but unless we give a path, there will be an EMF generated. One direction, one terminal will become positive, one will become negative, and if we join them, current will flow through it across a coil, and if they are connected, a current start flowing. A current flows. This is what I explained you. This is law 1. Simply, what happens by doing what? Then law 2. Law 2 tells us how much EMF is induced. It says the EMF induced across the coil is equal to rate of change of flux in the coil. So, what is EMF induced? Let us say it is EMF induced. This is equal to rate of change of flux. How do we write rate of change of flux in mathematics? Answer, we write it by d phi by dt. Rate of change of flux with respect to time. So, this is dB phi by dt, and these two are equal. That's all. But we find that the direction of EMF is opposite to the change of flux. So, we put a minus here. So, this is second law, E is equal to minus d phi by dt. Okay, we will do this in detail in the next law when we studied Lenge's law, but here E is equal to d phi by dt and negative. Okay, so these are the two laws. If the flux change, we have definite values that flux was phi 1. Due to certain action, the flux has changed to phi 2, and that action has taken time t. Then what is the change in flux? F2 minus F1, phi 2 minus phi 1, and how much time it has taken? T second. Then phi 2 minus phi 1 upon t. What is this? Rate of change of flux, and this will be EMF. This will be the EMF when flux is changing. Flux we know. It is B into A. So, we will see how the flux is changed with reference to this formula, but that we will do in the next lecture. So, this is Faraday's law, these two things, especially this is very important. This is very important, and we will keep on doing on this. Suppose I tell you there was a flux linked with a coil which was 20. Within 5 seconds, it has become 30. Flux linked to this was 20, within 5 seconds it has become 30. Then what is the EMF induced here? Answer is EMF induced, change in flux divided by time, 2 volt. So simple. So our galvanometer will show 2 volt. What is the unit of EMF? Volt. How much will be the current flowing? Answer is current flowing I is always equal to E upon R. So this we can say minus 1 upon R d phi by dt. This is for the current flowing in the circuit, And what is this R? This R is resistance of this device which is connected with the coil. So this is the Faraday's law's introduction. Now this EMF which is induced and the current which is flowing here, the current flowing, this has got a particular direction. What is the direction of this EMF? In which direction you would like to flow the current, this way or this way? That was given by Lenge's law. And now in the next lecture we will study Lenge's law, which is also very important. So the first law we have done is Faraday's law. Whenever there is a change in the flux linked to a coil and EMF is induced, with the closed circuit current start flowing. This is how we can get the EMF and the current. If you go to energy, then okay, we will discuss in the next lecture that what is the energy implications in this. Thank you.